Hello everybody! Continuing with the homebrew function generator, today we see another useful circuit, a voltage-controlled Sawtooth oscillator. Among other usages, it can be used for testing components and tracing their volt-ampere characteristic on the scope or with the plotter. It is therefore important the linearity of the ramp and a reasonable fast swing at the end of the ramp. So this is the occasion to see the application of the LM311 comparator, a constant current source using a single transistor, what are the factors that affect the frequency range, how to make a transistor to switch faster, and in general what to care about in the circuit for higher frequencies and wide bandwidth. Let's get started. After having tested the proof of concept on the breadboard, the circuit has been moved into this printed circuit board with superficial soldered components. It looks a bit of a mess because, after all, this is a prototype. A mistake here, a modification there. Anyway, this circuit works acceptably well now. It sports a frequency range between 6 Hz to 1 MHz, split in two ranges, low covering audio frequencies and high up to 1 MHz. The core part of this oscillator is given by the ramp generator, which is formed by a current source that charges a capacitor with a constant current, and a switch that shortens the capacitance when the voltage reaches a given level. Since the voltage across the capacitor is proportional to the charges that build up over time on it, providing a source of constant current, there is a constant flow of charges, and it is the way to go to generate a straight ramp. A fast comparator is then used to check when the voltage reaches the set level that is defined by this voltage divider to drive the transistor, this transistor that works as a switch, which quickly discharges the capacitor, and the net result is a ramp that at the set voltage suddenly falls to zero and start over again, repeating the cycle ad infinitum. That's it, simple. Now, because we'd like to vary the frequency of this oscillator, we have to change the quantity of current, the quantity of charges that charge the capacitor. In other words, the current that flows through toward the capacitors. Because the time is given by the voltage times the capacitance over the current, the lower the current, the larger the time it takes to charge the capacitance, and thus the lower the frequency. Looking at the current source, we can notice that the current depends by the voltage between the positive rail and the base of the transistor, this voltage here. And for those among you that don't know how this current source works, let's assume that the voltage across this resistor here is given by this voltage, the voltage between the positive rail and the base of the transistor, minus the voltage drop between the base and the emitter of this transistor. And I will make a video with more details to understand how constant current sources work, including the one with a single transistor like this. But for now, to make things simple, let's assume that this point, varying this voltage, will vary the voltage across this resistor, and therefore the current that flows toward this capacitor, and that is how we can control the current and therefore the frequency of the oscillation of this oscillator. So varying the voltage at the transistor's base, we can control the current, thus the frequency. Now let's have a look at the comparator. As we've seen, the constant current source provides the charges that make the capacitance to charge, to rise the voltage across it, and as soon this voltage reaches the same voltage given by this voltage divider, the non-inverting pin of the comparator, as soon as this voltage reaches this point, the comparator turns on its output, which is a transistor, and the pin 7 is connected with the pin 1, and because here we can have a maximum of a voltage drop between the base and the emitter of the transistor, which is 0.7 volt. Here we have to add a voltage here between the pin 7 and pin 1, which is the voltage drop of the internal transistor, which is about 0.3 volt, and then we have this voltage drop of this diode, which is 0.7 volt, which in total gives us here a voltage of about 1.7 volt, and this is the new voltage that changes after the comparator has turned on. The voltage here changes between the original level that was the peak of the ramp. It changes from 4.8 volt about to about 1.7 volt. So the ramp, the transistor will stay on, will discharge the capacitor until this voltage will reach us and will go below this voltage. At this point, the comparator switches again, opening its output and in turn turning off the discharging transistor, allowing the capacitor to charge up again and restarting the cycle. Also, applying every load here would affect this waveform, and so a buffer is connected here to isolate the output from this point to avoid this kind of problems. Okay, we have now a Sawtooth generator, but the attentive watcher would have noticed the problem here. We can see that the voltage applied here between the base and the GND, the voltage control, the lower this voltage, the higher will be this voltage, and therefore the current that flows through this transistor and to charge the capacitor, and therefore the higher the frequency, which is the exact opposite of what we want, because we want to control this voltage with a voltage from 0 to 10 volt, where 10 volt is the maximum frequency and 0 is the lower frequency. And furthermore, if this voltage goes below this point, this voltage here, the voltage divider here of the comparator, if this voltage goes below, this capacitor won't be able to charge to reach that voltage, and so it won't be able to reach the threshold voltage, stopping the oscillator altogether. So we have to do something to correct this. To solve this problem, we feed the voltage control to an op-amp, here a buffer connected as a non-inverting configuration as a buffer, and then we feed this voltage to this other operation amplifier, where we have this network that will change the gain of the operation amplifier, and you will notice that the voltage here is inverted. So when this voltage goes to positive, this voltage would go to negative. And to compensate this fact that it goes to negative, we have here a bias control that is used to correct the voltage feeding a negative current through this resistor and moving the whole voltage excursion, the whole voltage range from 0 to negative to 0 to positive. And this is a little bit tricky to adjust because we have the gain and the bias that act on the same operation amplifier, but it is in reality quite simple. First we turn this completely to 0 and adjust the gain for the full range of voltage required to control this transistor, about 4 volts, and then we adjust the bias in a way to correct this voltage and put the minimum voltage here at 4.3 volts. Okay, now we have a nice Sawtooth generator. So let's see how to make it to work at its best. First off, our circuit as it is now, while it is able to generate a nice Sawtooth waveform, it doesn't have a wide range of frequencies, as it starts from 50 kHz and reaches 200 kHz with a capacitor of 1 nanofarad, a frequency ratio of 4. While swapping the capacitor with 10 nanofarad, it doesn't work at all. Also, the ramp starts after a while, and this is clearly caused by a delay with a switching transistor that takes time to turn off, because the charges need to be evacuated from the base emitter junction. To solve this problem, we can bias with a negative voltage the base of this transistor to help drain the charges. Also, we need a diode to prevent the voltage going fully negative, causing a reverse bias avalanche between the base and the emitter junction. Also, this diode needs to be fast by itself in getting rid of the charges. So what we need is to change here, put a diode here, a fast diode, and here put a resistor connected to the negative rail. After this modification, we can see the transistor turns off remarkably faster. The frequency now starts from 75 kHz and reaches 268 kHz with 1 nanofarad capacitor. However, we can notice that changing the capacitor with 100 nanofarad, the voltage falls at about 1 volt, while with the 1 nanofarad capacitor, the voltage almost reaches 0. Why this happens? Again, the transistor isn't fast enough to switch. With a larger capacitor, there are more charges to remove, so for the same collector emitter impedance, a larger capacitor takes longer to be discharged. This means that some charges remains and we see them as a residual voltage. However, notice that the problem is with the smaller capacitance, because as the voltage falls below the comparator's threshold, while its output switches with a small delay, the transistor still has some charges stored in its base emitter junction, despite the negative voltage applied that should help in draining them out. So what we can do? Actually, we are not that interested that the voltage reaches 0 or remains at 1 volt or 2. What actually we are interested in is a consistent behavior between different frequency ranges. One possible solution would be to skip to change the capacitor altogether and rather change the resistor of the current source. But this solution is not flexible because with a large resistor the current would be noisy, and with a too small resistor the current would exceed the transistor capability. So the idea is a compromise, using smaller capacitors, say less than 100 nanofarad, and to expand the range of frequencies for the same capacitor. So what we have to do is to allow this range to be a little bit larger and use capacitors here that are below 100 nanofarads, that is the limit. So the idea is to use a capacitor of 100 picofarad here, and in parallel a capacitor of 15 nanofarad that is connected toward ground through a switch to change the range of the oscillator, and to increase the range, the voltage control range, we have to lower this voltage here, because this operational amplifier isn't able to reach the voltage up to the positive rail. So to lower this voltage a little bit and to stay within the range of the operation amplifier, we just add a couple of diodes here, a couple of diodes, silicon diodes, and here we have the positive rail, and so we have a fixed voltage drop here of 1.4 volts. Also reducing this resistor a little bit improves, allowing to have a larger voltage here. So this is the final circuit. We have changed the capacitors here. Here we have the 100 picofarad capacitor, and here the 15 nanofarad, two capacitors in parallel, one 10 nanofarad and one 4.7 nanofarad, because I don't have a 15 nanofarad. Here we have the voltage control through the potentiometer that enters here, where we have the 1458 operation amplifier, here the voltage follower, and here the inverting amplifier with the two potentiometer trimmers to adjust the gain and bias, and the signal then is fed through this resistor 100 ohm here to this transistor, switch transistor, and this is the transistor, the current source transistor, the resistor, the 5.6 kilo ohm resistor here, and the two diodes here to create the voltage drop. Sorry, I've melted this capacitor. Don't care. Don't watch this. and the output of the Sawtooth is fed into this half operation amplifier here, which is connected as a voltage follower, and the output is fed through this resistor to another part of the circuit. And here we have the comparator, the LM311 comparator that compares the voltage from the ramp here, resistor, and the other resistor of the voltage drop, the voltage divider, sorry, and here the 22K resistor that provide the current through the output of the comparator, and this blue diode is the Schottky diode. And here we have a switch that is used to change the range and to connect these two capacitors to GND to ground to change the range of the oscillator. And so let's have a look at the oscilloscope, see some waveforms. Okay, the output of the PWM generator, but this is a topic that we will see in another video. It is just for reference here. And let's change the frequency. We can go up to the maximum. Maximum is 1.1 megahertz, but as you can see, the signal is quite distorted at 1 megahertz. This is the waveform. This is acceptable. Of course, we are limited to the
fall time, because the falling time is determined by the transistor. We would need something better to have better performance. Here the time it takes to reach zero, from the top to zero, is 230 nanoseconds. Going down to the lower frequency, you can see we reached 840 hertz, but we are at the limit, because in fact we see there is a little bit of instability. Minimum workable value is about 10 kilohertz. Changing the range, we can see down to about 7 hertz, and the maximum frequency is 24.7 kilohertz. Well, if you have any question or correction or observation, please let me know in the comment section below. Also, my videos about electronics don't get much views, so if you want to see more about electronics, consider to share with your friends this video with your friends, and click the thumb up icon to help the channel to grow a little bit more. Okay, that's all folks for now. Thanks for watching. See you next time. Bye.